Okay, looks like we can get started. Well, thanks for joining us on a Thursday. Wow, you guys have made it this far in reInvent. Well done. I am Rudy Chetty, Senior Solutions Architect, also the official hype man for reInvent, so please check out our daily recap videos. But not to digress too much, we're going to be talking about how Amazon Key for Business built a virtual fob. So I'll be joined by my customers, Frank Lee and Taru Roy, both engineers for Amazon. So let's check out the agenda. Well, it's pretty simple for this. We're going to give you a bit of a refresher on Amazon free RTOS, that's free real-time operating system. We'll go into then the customer portion where Amazon Key for Business will talk about specifically the hardware they used and then dive deep into the software layer. And then, excuse me, we'll go and give you a bit of a demo through a video. We were going to do a live one, but looks like our props didn't make it to Las Vegas. So the refresher. Well, Amazon Free RTOS, it's an operating system that's been around for 15 years or so. It's widely distributed, trusted, and it's modular. You know, the architecture is such that you've got the hardware layer. On top of it, you've got all these IDFs. Likewise, the kernel and all these other parts of it that you can use as you want. You don't have to use the full spectrum. The MQTT agent, if you want to use that alone, you can do it. The shadow library, the OTA agent. We've got a community version, but when Amazon acquired the company, the creator also came across. So we've got the Amazon flavored version, which has all the cloud libraries. And well, actually, let's dive into that. So specifically, we have local connectivity libraries. So if you have edge devices, you have AWS IoT Greengrass in your ecosystem, even Wi-Fi capabilities you need, those are built into Amazon Free RTOS. Likewise, you can manage your Wi-Fi if you need to abstract the layer. The Wi-Fi features are right there, like setup, configuration, provisioning, and so forth. You've also got access to Bluetooth Low Energy, or BLE. That's if you want to get features such as GATT or GATT or GAP, you can get that with the Amazon Free RTOS operating system. You've also got these SDKs that you can develop with. You've got the mobile SDK, you've got the mobile SDK for both, I should say, iOS and Android. And it abstracts all of that away from you, so you don't have to do the so-called heavy lifting. Leave it to Amazon, and then you can get back to coding your application. And don't worry if there's no cloud connection; it still works. So if your connection is severed temporarily, or even maybe for a longer time, it'll still be up and running. And this is the part I mentioned here, or the cloud connectivity libraries, and this is where the power really comes in. Is that you've got the AWS IoT core, where you connect to provision devices, and that's your entry point into the AWS IoT ecosystem. And that's where you're going to provision a thing. And you can see in this case, the thing is actually sending one message to the core, and you're doing it via a MQTT publish subscribe. So that connectivity comes out of the box with Amazon Free RTOS. You just have to provision your certificates and keys, put them on the device, and then Bob's your uncle. You can go from there. And as you saw there, a publish subscribe it's a very easy way of doing one-to-many. So you publish once, and if you have multiple subscribers, as you saw with the thing, it's a coffee pot, and everyone's waiting for their morning coffee, or maybe right now you could do with a cup of coffee. Myself, tea, but over here, people are waiting for their cup of coffee and they want to get notified. They can subscribe to a topic, and in this case, when one notification is sent out, it gets dispersed to multiple subscribers. And you're thinking, well, what else do we have on offer here? Well, you have access to the shadow. So the device shadow, or thing shadow, if you think about it, it's a logical representation of state of your device in the cloud. And in this case, we've got certain parts that we want to highlight. So the desired state, that's what your device is reporting. So maybe there's an LED on this coffee pot, and it's blue. So that's reporting back to the cloud that, hey, I'm blue. And then, the desired state. You know what? I've preempted myself. The desired state is actually the other way around. It's what you want to tell the device to actually report. So the reported state is the one that's telling you, hey, the LED is currently red, but I want to change it to blue. Maybe you want to match your hoodies that you got for part of your AWS swag here for attending reInvent. So you're going to change it to blue. But reported, that's what the device is actually reporting. So if maybe the color was red initially, it'll report red. But then if you want to change it, you can actually say, oh, I want to change it using the shadow, and I set the desired state, and that'll change it to blue. And then another important part is the metadata. A lot of people use this for versioning, so you can see you can actually have the version tag there or version attributes, key value pairs. It's a JSON file, so it's very friendly to read and to actually modify. And you also have a timestamp. So if you want to know when that color changed from red to blue, or maybe when the coffee's ready, you have a record of that actual time when that happened. You also have security connectivity libraries. So I mentioned a bit of how you need to provision certificates and so forth. The certificate-based authentication is built in. So when you want to authenticate a device, you can provision the certificates, and like I mentioned, you just copy them to the device, and device is up and running. It can connect to the AWS IoT core. Obviously, you need to enable those certificates once you provision them. And to give you an idea of what they look like, you can see it's not something that's easily reproducible. You've got the begin of the certificate, a bit of a tidbit, and then the end of the certificate, and that's a unique certificate for you. So your devices, we recommend that when you provision them, provision one per device. Because if you ever need to decommission that certificate, if it's associated to multiple devices, you might have to decommission all of them in one go, and you don't want to do that. This is an example of how you would create it using the command line interface, or CLI. So AWS IoT create keys and certificates, and you can see here, I'm actually naming the files. In this case, I've put certainly, for a bit of a pun, if you know what I mean. And we're doing the certificates and the private keys and the public key, and you can see I've given it similar naming scheme across the board. Also, with Amazon FreeRTOS, you don't have any open ports. You're using TLS, secure sockets as well. And if a port is not open, it's not going to be open unless you actually go in and open it. So no network ports, and like I said, secure sockets using TLS. Also, you get the benefit of actually running trusted code. So if you deem a particular batch of code non-trusted, you wouldn't be able to run it against your device. So it's, as I mentioned, only run trusted code, and it's that clear modular implementation. And then this was on one of the other slides as well, the OTA, or over-the-air updates. That's what comes out of the box. So you can provision your updates to groups. So groups of devices, as I mentioned, if say we had all the lights here running on Amazon FreeRTOS, we could update them in one go by using groups. And we can also sign the firmware images. So again, we want to make sure that we're only running code that's trusted. So sign that firmware image, make sure it's only coming from a trusted source and so forth. And then you can stream the update over MQTT. So messaging, queuing, telemetry, transport, you can stream the update. And if the update fails, it'll roll back. So that's also nice. And you've got APIs for installing on the device, and obviously rebooting, because if you're going to update, you probably want to install and then reboot and make sure that the device comes back online. And as I mentioned, you can update groups, but again, you can assign groups that are logical. In this case, you can see this would probably be a transportation group. So if I needed to do an update, I can update my whole transportation group, or I could make another group that's just bicycles or just cars, and I can update those accordingly. Because obviously, I probably want to send a different update to bicycles versus cars, unless they look the same. And in this case, we've got another one, which is aeroplanes. And the last thing to touch on here with Amazon FreeRTOS is the Device Defender library that you have. So AWS IoT Device Defender is another AWS product in the IoT portfolio. And what it does is, excuse me, you can audit and you set up these policies, and then you monitor your devices. And you want to make sure that there's no bad actors trying to gain access to any of your devices or maybe compromise it. And if something happens, you get alerted. And obviously on that alert, you want to make sure that you take an action, so you want to mitigate. Maybe you want to take that device out of commission, maybe you want to rotate its certificate, maybe you need to install a firmware update. You even have access to device-side metrics. So things such as maybe CPU utilization, memory, TCP connections. Maybe a certain device is only supposed to have 2 TCP connections and it's got 5. You're thinking, what's going on there? And then likewise, you can detect these anomalies that are happening. So as I mentioned, maybe it should only have 2 connections. And then, if something happens and your device has been compromised, maybe it'll look like this little robot, firing off stuff because your device has now become a bot. But because you have anomaly detection, you can catch that early and you can actually mitigate on it and take that device out of action and so forth. But you know what? You're here to learn about Key for Business and how they built it. So let me give you a bit of a preview of that before I bring up Taro. So, the what if, what, who, where of the problem was that you have a source and destination. So when you go in, you click order on Amazon, purchase an item, and you're going to send it from the source to the destination. So to your house, your apartment, flat, and whatnot. And this was normally done by third-party drivers, like FedEx, UPS, and so forth. But then Amazon thought, well, can we bring it in-house, make something that we can use, or we can do for our customers, bring it closer to home. So they created last mile. So that's quite literally the last mile of when the package is going out to your house, or as I mentioned, flat and so forth. And they kind of got to the point where, they go to a place, they're trying to deliver the package, and they're like, wait, I can't get in. It's an access control building or an access control property, whether it's commercial or residential. And they're thinking, well, how do we solve this issue? Well, the first part of it is to think of a solution, but also you want to prototype. And the way the team went about prototyping is they went straight to what we call the AWS Partner Device Catalog. So that's a catalog of qualified devices that are qualified with either Amazon FreeRTOS, Greengrass, and they're qualified to actually connect to the AWS IoT core. They have that cloud connectivity that's been validated, tested, and these devices, you can go in and purchase them, and these kits are good to go out of the box for prototyping, or if you want to take it further. They chose a kit that was using Amazon FreeRTOS, so they didn't have to do that heavy lifting of building their own operating layer on the device. They also chose a device that they could plug on components. So in this case, they wanted to plug on cellular connectivity, Bluetooth. They even wanted to put a building access controller on the device because, again, we want to give drivers access when they need to deliver a package. And that's what they went about doing, and they picked a device. And then they ended up with this kind of architecture. Now you can see there's quite a few components here. And as this is the preview, I'd like to ask Taro to come up and you know what? He's going to deep dive in the hardware, and then you'll learn a bit more.
Thanks, Rudy. So a little bit of context about the Key for Business. We are a team within Amazon, and I guess Rudy already mentioned what we're trying to do. And it is essentially to help our customers get their packages delivered on time. Now, the way we do that is by allowing Amazon's delivery drivers to gain entry into access-controlled buildings or package rooms using their mobile phone. We also have an internal customer, which is Amazon's last-mile delivery team. And the major problem that we solve for these guys is what they call as unable to access. So if the driver is waiting too long to gain entry, what they have to do is to go back to the station and return again the next day to redeliver. And the way we have solved this problem is we have solved it by having what we call as a cloud-connected virtual key fob, which was built by our hardware team at the Key for Business. It's a very small team of about 2 people when we started. And what the device does is it's taken to the premise location of the property, and it is installed there physically. All these properties have their already existing access control systems infrastructure that they use to manage access. So what a device does is seamlessly integrates with all kinds of access control infrastructure. And once it's installed, the property owner gives a credential to our device. The device stores that credential, and when commanded over the cloud, it presents that credential to the access control system to authenticate itself, and then requests the access control system of the building to unlock the particular door. So in the next few slides, I'll be talking about how we architected this device using Amazon FreeRTOS on the device side and AWS IoT Cloud, AWS IoT Core on the cloud side. But before we go over, let's talk a little bit about the kind of cloud connectivity we had to look into. So we first looked at Wi-Fi. Because we were installing the devices at these buildings, we had to figure out what kind of communication channel is the best. We didn't choose Wi-Fi because it would have meant giving a companion app for Wi-Fi provisioning in case the Wi-Fi passwords changed. We looked at BLE and did not end up using it after prototyping because it presented a challenge for positioning the device. It needs to be close enough to be in range with the driver's phone, but it also needs to integrate with the existing access control system. We started with Ethernet. We developed a device using Ethernet connectivity from Microchip. We got that right out of the box, and we created a device, started installing them, and realized that it's not as readily available as we thought earlier. So we ended up using cellular. We did not start with cellular first because Amazon FreeRTOS did not provide it right out of the box, and we had to get this product out in the market really quickly. I'm not sure whether it even provides it now, but that might change soon, and you might see Amazon FreeRTOS coming out with a public offering of a cellular connected device. And earlier, we also thought that it might be significant development work. When we actually started working on it, we realized that it wasn't as much work as we thought it to be. Because of the way Amazon FreeRTOS libraries are structured, it became really easy, and I'll talk about that, how we implemented the cellular solution into our product. And finally, there is this link which you could go to and look at all the hardware and all the kind of communication channels that they support right out of the box. So let's talk about a little bit about the cloud side, which has the AWS IoT Core and some of its features. So these include mutual authentication between the device and the cloud. And what that means is that not only does the device authenticate the cloud, for which it requires a root CA to be embedded in the device and is publicly available, so that's pretty simple, but it also requires the cloud to authenticate the device. And what that means is that the device needs to now have a device certificate and a corresponding private key, which needs to be securely managed and provisioned onto the device. I'll talk about how we solve that issue of securely doing it in a later slide called key provisioning. It has communication using MQTT broker, using a publish and subscription model. It is kind of similar to HTTP, but it's much more lightweight. And unlike HTTP, which uses a request response kind of a model, uses publish and subscribe. It has permissions, which means that you could tell your devices that they can only connect to certain endpoints, or they could only publish and subscribe to certain topics. They have device management using something called as device IDs, or in AWS IoT terminology, something called a thing name, using which you could make groups and then do an OT on the entire group, for example, or set permissions for the entire group. Then there is analytics, so you could send the devices data to IoT analytics, process them there, and then connect them to AWS QuickSight for visualization. And then there is the IoT rules engine, which I would like to talk about a little more in detail. So what the rules engine does is that you could, any kind of data that is being published on your topics, you could get them using a SQL-like query, and then all that data you could stream into various AWS services. For example, in this case, we have a topic of the form SomeString/updates, so that SomeString part has been depicted by the plus symbol. And we are taking all the data that has been published on that topic, as well as some metadata, which is represented here as topic _1. And what that is just the topic name, which is represented by that plus symbol. So we're taking some data and some metadata, and we could route it to various AWS services. For example, we could put that in DynamoDB or S3. We could also publish it to another IoT topic. We could push SNS notifications to get emails or SMSs. send to IoT analytics, and even trigger a Lambda. So a real-life use case that we used for AWS IoT rules engine using Lambda was when our device was being provisioned, actually productized in the assembly line, we want to do a very last sanity check to see that once the device has been assembled, does it actually connect to the cloud, and can the cloud command it? To do that, when the device would connect for the very first time in the factory, it would publish some data on this topic. And when the data was published, what we would do is get that metadata, which would give us the thing name or the device ID of the device that was actually pinging on the topic, and set up an action for a Lambda trigger. And within that Lambda, because we had selected the topic in that SQL query, the Lambda had access to that device ID name. Using that device ID name or the thing name, it could now know and create a topic which it knew the device was listening to for commands. And it could send a command to that device on that topic. For our particular use case, that command was as simple as turn on an LED, for example. And so the operator at the end of the line would power on the device, it would connect to the internet, publish to this topic, and would get a command from the Lambda automatically to say, hey, turn on this LED, and the operator would know then that everything is A-OK. Next, moving on to the device side, using Amazon FreeRTOS, Rudy talked about a bunch of libraries that it has to offer, like MQTT, PKCS11 libraries is another one which is used for key management, and I'll talk about that later. There's OTA agents. There are a bunch of other useful libraries, and the main reason we used it on our device side was because our business logic was not that intensive, and we wanted low-cost MCUs to be able to accomplish our tasks. And Amazon FreeRTOS allows us to do that because of very low CPU and memory requirements. It also allowed us to get really fast into the market because it does all the heavy lifting for security and OTA. Speaking of OTA, for example, I just wanted to get into more details of how it's done because I think it's very important to get it right. Once you have this done, what you could do is release your product quickly and then fix bugs or release new features later on. And having this done correctly is very important because you don't want to break your devices when you're doing an OTA. So on this slide, for example, on your right, this represents the device side of the things, and on the left, it represents the services on the cloud side. So on the device, as you can see, there is the MCU, which is running Amazon FreeRTOS, and it's also running the OTA agent from Amazon FreeRTOS. The main application is running from a Flashbank 1. There is also a Flashbank 2 memory, and to do a robust OTA, your device should ideally support 2 flashbanks. Oh, on the cloud side now, we have the AWS IoT Core service. We have Amazon S3 on which you can upload your new firmware that you want to OTA. And there is the AWS Key Management Service, which has the OTA private key. So, and the corresponding OTA public key is on the AWS device, the IoT thing. So the OTA private key and the public key were created once in the beginning, and the device was provisioned with the public key, and the private key was stored in the KMS. Just to make things clear, these are different keys from what I talked about in my previous slide, where I said that the device needs to store the private key to authenticate itself to the cloud. Those keys are being used for mutual authentication between the device and the cloud, whereas these keys are being used for authenticating the firmware image itself. So these 3 services, when you try to push a OTA image to the device, talk to one another, and ultimately create and send a packet which is composed of what we call a header at the top, the firmware binary image itself, and then the signed image of the entire thing, the signature of the entire thing at the very bottom. And that signature is created using the private key. Once it reaches the device, the main running app captures it and flashes it into the different bank, which is not running right now. Once the entire image has been flashed, the MCU authenticates it using the OTA public key. And if it is authenticated, it marks the header of the new image as a newer image, and it still needs to undergo what we call a self-test. And then it reboots the device. When the device reboots, first the bootloader runs, it checks for the 2 banks and figures out that there's a newer image based on the header. and sees that that new image needs to be tested first. So it boots up the new image in a self-test mode. The new image performs a self-test, and this could include a variety of things. For example, whether it connects to the internet or not, or you could write your own custom function to say, perform these kind of checks on the hardware when the firmware runs. If it passes the self-test, it marks the header as a valid image, and the execution continues. If it fails the self-test, it marks the header as an invalid image, and then resets the device. Now when the device would reboot, the bootloader is again going to see two firmware images, but it's going to see the new one as an invalid image. So it's going to still run from bank one, which had the older but a valid image. So this way, your device is never going to break during an OTA. I talked about how we implemented cellular connectivity onto our device. And another thing I wanted to talk about later is the key provisioning. And mostly I chose these two topics essentially because when we were developing our solutions, we did not have a full-fledged answer to these things from Amazon FreeRTOS. And again, those might change right now or maybe within a few months, and they might come out with their own offerings. But I would just like to talk about how we implemented the cellular connection. With Amazon FreeRTOS, the current chain of execution is like this. You have your application running. Whatever data you send goes through the TLS stack of Amazon FreeRTOS, which then goes through the secure sockets, which is like a BSD-like socket implementation, or a wrapper, which currently uses TCP/IP functions from Amazon FreeRTOS. So till here, it creates the TCP packet, and then it uses the driver, whether it's Wi-Fi or Ethernet, and sends it along the way. The problem that we saw while trying to implement cellular was that all the implementations that we came across required the TCP/IP stack to have a network interface for point-to-point protocol. And TCP/IP stack of Amazon FreeRTOS does not support this interface. So what we did instead was that we kept the application and the security layer exactly as it is, so that none of the security or the key management stuff changed at all. But in the secure sockets layer, we changed the functions to remove the TCP/IP stack functions for FreeRTOS and instead put the AT commands, the corresponding AT commands, in the secure sockets functions. And then that would basically send all the data to the modem using a USB or a UART driver. And we replaced the TCP/IP stack from Amazon FreeRTOS, but we use the TCP/IP stack of the modem. And the last thing I wanted to talk about was credential provisioning. So the main problem here is that if you guys had to look through the documentation or go to the console and try to make your own IoT devices, and they're very good for kind of getting you started because they want to be as simple as possible. But if you have gone through them, what you would have to do essentially is either on the console or using something like AWS CLI or SDKs, you would need to create your IoT devices first on your console. And this would mean create the thing name, create the certificates, attach policies, and then the biggest thing would be to download these device certificates and the private key. So now if you consider like provisioning millions of devices, you have to download all these device certificates and private keys, and it's not a secure thing to do really. You don't want your private keys out exposed. And then you have to manage how do you provision them securely in your factory. You need to flash all these device certificates and keys which are unique for each device in your device in the factory during production. So we solved this issue by also another service provided by AWS IoT itself called the just-in-time registration or just-in-time provisioning. They're pretty similar. The only difference between them is that the provisioning asks you to fill out a template, whereas just-in-time registration asks you to create your own Lambda, which gives you more custom control over what kind of devices are allowed to connect. And the basic difference between just-in-time registration and just-in-time provisioning versus the traditional method of downloading and flashing the keys is that in the traditional method, you need to create stuff first, and your devices might not exist, and then figure out how to provision the devices. Whereas in the just-in-time registration or provisioning world, the devices, the backend or the AWS IoT core doesn't have any idea of what the devices are, and the device first connects to the AWS IoT core, and that is when it decides that, oh, this is a new device that is actually authenticated, and allow it to be created and attach the certificates and create the policies for it. So the way we solved it in Key for Business is by having something called a secure element. A secure element is a physical device that created that private and public key pair for us, and it stores the private key within itself. In this case, we used secure element from Microchip called ATECC608, and embedded that chip with our MCU. So our MCU can communicate with it. And now to communicate, to allow all this to seamlessly integrate, this is where the PKCS11 libraries from Amazon FreeRTOS come into place. And what they are essentially are standard functions that you need to fill in. And in our case, we had to fill them in with basically I2C drivers so that it can communicate with the secure element. Once we have that in place, another thing, the last thing that we actually also need is a signer certificate. You could create your own, or you could buy it as well. So the first thing, and after that, everything is in place and we could get started. So all you need to do essentially is register this signer certificate at AWS IoT Core. And if you are using just-in-time provisioning, then you might have to set up the template as well. Once this registration is completed, essentially you could offload everything else to other service providers. For example, in our case, the secure element vendor that we used did everything rest for us. And that included the secure element, which is now part of our device, creating the public-private key pair. And the private key is always stored in the secure element, never revealed. But it sends out the public key, and then you could create a certificate signing request using the public key, send it to the signer certificate, and the signer certificate signs it, and now creates the device certificate. So earlier, the device certificate was being downloaded from IoT console. Now it's being created outside of it. Earlier, private key was being downloaded from IoT console. Now it's generated within the device and is never revealed, and nobody can have access to it. So now this signer and the device certificates both have to be embedded into the secure element. And all this thing, apart from registering the signer to the AWS IoT Core, is done by our service provider that provides us with the secure element. Once this is done, all the device needs to do is to connect to AWS IoT Core, and the AWS IoT Core realizes that it has the signer certificate that is already registered. Then it verifies that it has the same device certificate that is signed by the signer certificate, so it can say that, yes, I trust the device as well. And this is when it decides to trigger either a Lambda in case of a just-in-time registration, or use your template in just-in-time provisioning to decide what to do next. And then you could create your own things to say when the device connects, please allow it to register. Please attach these kind of policies to these kind of devices. And your provisioning is basically done. So your AWS IoT Core doesn't know anything about the device. You provision the device outside. It connects for the very first time to the cloud, and it's provisioned and registered automatically. So that's it from the hardware side. Next up would be, frankly, from Amazon's last mile delivery team, and he's going to talk about the backend architecture with you guys. Thank you.
Okay, thank you, Taru. Hello, everyone. My name is Frank Ni. I'm from the Amazon last mile IoT team. In the past 30, 40 minutes, you guys already learned a lot from Taru and Rudy. So in the next 15 minutes, I'm gonna talk about how we send messages from the cloud down to the edge device, and how do we connect the driver's smartphone app to the backend services, and also how we synchronize the data from different databases. So let's get started. So how do we send messages down to the edge device? So we use a Lambda, which is a service provided by AWS. And we compose and publish the messages to the MQTT through the AWS IoT Core, and then send these messages down to the device. So how do we send MQTT messages? First, we translate this payload whatever we want to send to the device into a Java class, which in here we call the ACU message, MQTT message class. Then next, we serialize this Java class into a byte array and then wrap it with the byte buffer. Now we can start to construct this publish request class. So in this class, we need to provide the IoT topic, which we can get from the IoT core, and then we set this payload as the byte buffer we just created, and then with the QoS, then we start to trigger this publish. Once we trigger this publish, the IoT core gonna send this message based on the QoS 0 or 1, depends on whatever we set, and then publish this to the down to the device. The last, we're gonna check the response from the SDK to make sure there is no error and handle it if there is any. So in our use case, we need to manage the different version of devices into different AWS accounts. So that basically means we need to send MQTT messages to different accounts. How do we do this across the account access? So first, let's think about this. We name this AWS account, which has the devices in it and where we want to send messages to as a trusting account. So in the trusting account, we first need to create an IAM role, which allows the corner to be able to assume this role. And then in here, as you can see, we name this principal as the trusted account ID. We will introduce this trusted account soon later. But here, the key thing is we need to put this assume role into the action so that this role is able to let trusted account assume it. Next, we need to create a policy. Because we want to send MQTT messages, so we need to put this IoT publish action into it. If you want to do any other actions, you can also put in here. And the resource is the one for the IoT topics which we want to publish message to. So now let's move to the trusted account. The trusted account is the one who's gonna construct and send this message, this MQTT message. So in here, you can see we have a lambda in this trusted account, which this one gonna send the message. When we create this lambda, we need to remember to assume this role that we just created in the trusting account for this lambda. So as you can see here, this execution role contains a resource which contains this trusting account role we just created. The last, in the code, when we create this IoT data client, we need to provide the credential which created from this trusting role we just created with the expiration time and also the connection time. Then we can use this IoT data client to publish the MQTT message same way as we did before. Okay, now we send the messages from the lambda down to the edge device. How do we connect the driver's phone to our backend? So we use the API gateway in here. I will not go in detail about how we create an API gateway in the AWS. Instead, I'm gonna focus on one key functionality for our application, which is authorization. Because for us, we don't want anybody to be able to access our API gateway. Instead, we want driver which has the valid login so that they can access our API gateway. So first, we create a cognito user pool which manages all of the driver's identity, including the username, password, the group. And then in the API gateway, we can create a customized authorizer. So in here, as you can see, we provide the cognito user pool in here, define this token source as a authorization. This one is the key. We're going to use this token source later on in the code. Then we move to the API resource. For any method resource we created, we have two options here. One is the AWS IAM, which provided by the API gateway by default. And also you can see here, the list has another customized authorizer we just created. So once we publish this method into the release stage, we can go to the SDK generation tab to generate the SDK for our mobile platform, either Android or iOS. So the package generated by the AWS API gateway has well-documented a README file, which you can follow it. It provides a step-by-step on how to integrate this API gateway with your application. So if we choose the IAM, so if we choose the IAM for our authorization, then it's gonna be a little bit simpler because we can just follow that instruction in the README file, provide the cognito identity pool and the region. Then we can create this API gateway client factory with this credential and then trigger our method. But this way, we cannot identify individual driver because all the driver cannot behave the same. To us, we need to be able to identify each individual driver. So what we do is we use the cognito authorizer, which we just created previously. The implementation is going to be a little bit different because this time, when we create this API client factory, we have to give this token to the HTTP header. So we can get this token from the driver session. Whenever driver log into the cognito with their username and password, we can get the user session. There is a JWT token associated with that session. Once we get this identity ID, we put this into the HTTP header with this authorized key. This is exactly the key we provided previously to the API gateway as a token source. So with that, then we can construct this HTTP request and then trigger our API method. So the last step is we connect this API gateway with our Lambda function. So now we can send a message from the driver's smartphone app all the way to the API gateway, and then pass this through the Lambda, and Lambda will compose the MQTT message and send this down to the edge device. OK, so now goes to the database. We use DynamoDB to manage all of the device information because the DynamoDB provides us the very low latency, the cost efficiency, and also the scalability. But we also want to do some analytics. For example, we want to do SQL query to generate a business metric, to check the status of our device, and also do some other stuff. So how do we synchronize the data between different databases? So first, if we just use simple schema of our DynamoDB database, for example, there is no map, there is no any kind of a connection, it's easy. We can just use the Redshift copy command. Trigger this in your Redshift, and then run this periodically. Then you can synchronize the database. However, in our case, we do have a map and some connection type of the primitive data we want to synchronize. So what we do is we choose the AWS data pipeline. So data pipeline provides a very good template where you can just follow it and then export this DynamoDB data into the S3. You can also define your own scheduler to run this periodically. And then you can trigger or bring up this architecture view to change your DynamoDB throughput to have a less impact to your production line. Once you get this database into S3, the next thing you want to do is trigger your Lambda function, which flatten your database. Because you have a map there, but SQL database doesn't support map. So what you want to do is flat this into the format what do you expect, and then send this data into the Redshift. Also, the Lambda function can be triggered by Kinesis event, so we can also do the schedule. So you already know that we use rules engine in Taru's presentation a lot. So we basically triggers Lambda to do the provisioning. We also trigger the Lambda for the production on the production line. In here, we also use the rules engine to basically route this device information into our backend, and in the end, put this into our Redshift table. So this device information, including like periodically update the device status, anything device triggered and sent to our backend, we can use rules engine, route this to Kinesis firehose. And in the firehose, you can easily set up this to connect with your Redshift database. So you have a table in there, and then once rules engine receive it, you will route to the Kinesis, and the Kinesis will automatically write this into your table. Then you can perform any kind of SQL query you want. OK, so with that, if you still have some confusing or doubt about this product, let's take a look at this demo.
Apartments, office buildings, and gated communities can now enjoy the ease of Amazon delivery with Key for Business. This all-new system gives delivery drivers convenient authorized entry to apartment lobbies and package rooms. No more buzzing in delivery drivers or bringing in packages. Key for Business integrates seamlessly with your building's existing access system and lets you and your staff spend less time managing your residents' deliveries and more time keeping them happy. Current residents will love having secure and convenient package deliveries right to their door. Every package is tracked and authenticated for its scheduled delivery before access to the building is granted. Key for Business. It's delivery made easy.
OK, so with that, I'm going to invite Rudy come back to the stage. Thank you.
Well, Frank, I think I've definitely found the key to my package delivery problems. Well, look, I know everyone's itching to go to lunch, so we'll wrap up with just some resources. So if you want to further your IoT journey, please check out this AWS IoT workshop. It uses an ESP32 microcontroller. It helps you connect with Arduino. You provision certificates, your certificate and private keys, public keys. Then you put them on the device. You can connect to the AWS IoT core. And from there, you create a Lambda function. And that Lambda function will be triggered when you simulate, say, a temperature spike on your device. So if the device reaches a certain temperature, kick off a Lambda, and that Lambda will send a notification to an Amazon SNS topic. And in that case, it could be your cell phone number, so you could send an SMS, or it could be an email address, so you can send it there. And if you want to go even further, check out these resources here. As I mentioned, the partner device catalog, where you actually get to go and check out devices that are qualified for the platform. Amazon FreeRTOS information here. There's a few episodes of a show called IoT All the Things, where we go into details about industrial IoT and also Key for Business. We actually demo one of the fobs on the episode, so that's pretty exciting. And then there's a building blocks presentation if you want to get a breadth of the services that we have on the IoT service portfolio. And then if there's any information that you need on the thing or device shadow, you can go check that out. And you know what? I'll do one more. So like I mentioned, with that particular button, we also have IoT buttons. So you can get those on Amazon, and those allow you to get started pretty easily as well. We have the one-click, which are enterprise buttons. So they have a certificate built into it. They've got a certain amount of clicks, and they will connect to the IoT one-click service, and you can use rules and Lambda functions to trigger events. So I always tell people that they have 3 clicks. So you have a single click, you have a double click, and you have a long click. And the easiest way to remember that when you're thinking about these IoT buttons and how to apply them is, say you're sitting at work late and you're thinking, you know what, I think it's time to go home and I better let my spouse know. And in my case, it's my girlfriend. So I'll say, let me push the button once and it'll go through Lambda, send her a message, say, you know what, I'm on my way home. Maybe you're sitting there and you're thinking, I could really go for a drink with the guys or my colleagues. So you double click, sends a message to say, you know what, I'm going to actually go out with the fellas, we're going to get some drinks. But if you're not going home ever, that's where you hold the long click. It tells you you're never coming back. But that's an easy way to remember that you have 3 different clicks. And with that, I will let you guys go early. And if you have any questions, please see us outside so you can get to lunch. Thank you very much, and I hope you've enjoyed reInvent and this talk.